All right, welcome to section 3.2 video. So in this, we're going to basically extend upon the conversation from the prior section 3.1, and we're going to look at graphs of functions. So even though in the textbook, the conversation in 3.1 didn't really focus on the graphs of functions, I did use Graphing Calculator, Desmos.com, and Wolfram to do a little bit of work for us. But that really was not the intended conversation in that section. So in this section, you're going to notice that the author focuses a great deal on the graph of the function and really reading information from the graph. All right, so let's take a look at a couple examples together here. So first thing we're going to look at here is a table of data. All right, so this would be like ordered pairs on a graph. And this data that we're given here is the price of gasoline in California for each year, the average price of gasoline in California for each year, starting in 1978 and ending in 2005. And this is a rich set of data points. And what I just want to kind of illustrate with this example is that it can sometimes be difficult to really glean information, if you will, right? Read this data set and see patterns. So most people in the world are very visual learners, and even if you're not a visual learner, the graph of this data set is much easier to see trends and see what's happening with the data set. So here is the data set graphed, and we can very easily see periods of time where the price of the price of gas was increasing. Notice this first piece here, it's increasing. The average price stayed relatively constant between these years. The price of gas decreased. Looks like we increased really sharply over here. We can see kind of this point looks like it might have been the smallest average year. Looks like this was maybe the largest average year. This one comes pretty close. So graphically, it's very easy to see very quickly trends where it's increasing, where it's decreasing, where it might have a max value or a min value. So again, the main purpose of this section is to discuss the graphical representation of a function, right? And in this particular example, we looked at the relationship between the particular year and the average price of gas in California. Now let's take a look at a couple other examples similar to what you might see in the homework here. Okay. So first of all, you've probably seen this term before, and again, this author is going to assume you haven't. So he's introducing to you the idea of the vertical line test. So let's suppose we are given a graph of a relation. Now, so remember our first conversation in 3.1 was that if we had a relation, how could we determine if it was a function? And we had the definition that for each x, there's one and only one y value. So visually, we can use what's called the vertical line test to test whether that definition holds true. Right? So in this example, we see two graphs that are relations. And if we apply the vertical line test, what we notice is this vertical line intersects the graph at only one point. Or this vertical line intersects the graph at only one point. So then we could really deem that for all vertical lines, right, this graph represents a function. Ditto for this guy here, right? So if I think of all possible vertical lines crossing through this graph, each instance of any vertical line is only going to intersect the graph one time. So we're going to call this relation a function as well. And that's what I want to point out to you visually here is that, when I draw a vertical line, in essence what I'm doing is I'm picking an x value and I'm seeing how many y values pair with it, right? So if I draw a vertical line and it intersects the graph at only one point, then for each x, there's a one and only one y value. And then on the other end of the spectrum, right, here's an example where a vertical line intersects the graph more than one time. And again, visually, we're picking an x value, and we're seeing that there's more than one y value paired with that x value. So this fails the definition of the function. So this relation is not a function, and visually, it's failing the vertical line test. And ditto for the circle over here, right? So we can see that this equation represents the circle, and each x, right, has more than one y value. We would say this relation, not a function. All right, so if I give you this example, right, and I say determine whether this graph represents a function, what would you say? All right, so even though I couldn't technically hear you, I think everyone said that this graph is a function. So if you said that this graph is a function, excellent. So I'm going to think of every vertical line that passes through this graph is going to intersect it only at one point. If I draw a vertical line right here, it's going to intersect at only one point. If I draw a vertical line right here, it's going to intersect only at that one point. So this graph passes the vertical line test. I would call this relation a function. So what would you say about this graph? All right, well, excellent. If you said that this is not a function, good answer, right? So here's one example of a vertical line that's going to hit the graph twice. So I got one intersection here, one intersection here. So this relation does not represent a function. It fails the vertical line test. All right, so in this section, again, we're talking about interpreting visually, right, graphically about graphs and functions. So this was the first concept that we would talk about. So the second objective would be to obtain information from the graph. So we're going to dig a little deeper and look at information about the graph. So this problem here, this example that we're going to look at has multiple parts. So let's take a look at it one at a time. So here's the graph of a function, right? First of all, I know this is a function because the problem is telling me that it's a function, right? But I also know that it's a function because it's going to pass the vertical line test. Any vertical line is going to intersect the graph at only one point. I draw any vertical line here, it's going to cross the graph at only one point. So this graph passes the vertical line test. It is a function. So part A says, is asking us to find three different function values. So the first one we're being asked to find is f at 0. So just like we did in the prior section, remember this is asking me to plug in x equals 0 and find the y value, right? So I'm going to come over here to the graph and let's see, I'm going to pick x equals 0. Here's x equals 0 right here, and I'm going to find the y value. So f at 0 would be 4. Then the next one says find f at 3 pi over 2. So again, I'm going to plug in 3 pi over 2 into my x value, find the y value. So let me come on my graph. Here's 3 pi over 2 on my graph, and I can see my y value is 0. And then the last one being f at 3 pi. So again, I'm going to plug in x equals 3 pi. Right? Here's x equals 3 pi right here, and I can see my y value is -4. So there's the three function values. F at 0 is 4. F at 3 pi over 2 was 0. And then f at 3 pi was -4. All right. So again, in this section, what the author is going to do is take away the equation. He doesn't want you to be able to plug x equals 0 into the equation. He wants you to read that information straight from the graph. So letter B says, what's the domain of the function? Now remember that in the prior section 3.1, we talked about if we had the equation, how we could determine what the domain is. And one of the things we talked about was that for each x, there's a real valued output. So what we're going to look at for this graph, right, we're going to look at really where does the graph live, right? Where are its outputs? Where are the y values, right? But when I'm asking for domain, I'm asking what x's produce those outputs. So you can see in this graph, there's a point here where the graph stops and it doesn't continue on in this direction. So from the graph, it appears that x equals 0 is the smallest x value. And then it appears that as I move along the x values, there are y values being plotted all the way up to the x value of 4 pi. And then again, there's a point here, and the graph doesn't continue in this direction. So I'm going to assume that this is where the graph stops. So the domain looks like it's from 0 to 4 pi. I could write that in set builder notation, or I could write it in interval notation. And the next question is, what is the range? So again, this is the y values of the graph. So if I'm looking at all the y values, notice that -4 is the smallest y value and +4 is the largest y values. And all the other y's are plotted in that interval. So I'm going to say the range is -4 to 4. Right? And again, here's my set builder notation, and then here's my interval notation. All right, the next question says list the intercepts. Now you gotta be a little careful with this question because it's not saying just the x-intercepts and it's not saying just the y-intercept. It's wanting both groups. So it wants the x-intercepts and the y-intercepts. So the first intercept here, the y-intercept is 0, 4. So I'm going to list that one. And then here's all the x-intercepts. Here's the first x-intercept, pi over 2 comma 0. Here's the second x-intercept, 3 pi over 2 comma 0. Third x-intercept and fourth x-intercept. So I'm going to make sure I list all 5 of those intercepts as given on that graph. All right, letter E says, how often does the line y equals 2 intersect the graph? Now remember, this is a horizontal line right at y equals 2. So I need to plot the graph y equals 2. So there's the line y equals 2. And then how many times does that intersect our function? So it looks like 1, 2, 3, 4 times it intersects our function. All right, so letter F says, for what values of x does f at x equal -4? Now, letter A, I want to point out to you, we were plugging the x value in, finding the y value. But in this case, what we want, we're finding the x value that makes the y equal to -4. So if I come up to my graph where y is -4, here's one value where y is -4. That would be x equals pi. And then here's a second value where y is -4. That would be x equals 3 pi. So I got 2 places on the graph where y would be -4. All right, and letter G says, for what values of x is f at x greater than 0? All right, now let's interpret this for a second, right? So if f at x is greater than 0, remember this is the symbol that represents the y's on the graph. So this is saying, for what values of x is the y greater than 0? Now also remember, if a number is greater than 0, it's a positive value. So right here is where all the y's are equal to 0, right? Here's y equals 0, y equals 0, right? Y equals 0. Down here is where all the y's are less than 0, right? They're negative. And then up here is where all the y's are greater than 0. So what I want to do is I want to find all the values of x for which the y is positive. So here, this first section right here, all the y's are positive, right? Now this question is saying, what values of x make that true? Right? So any x between 0 and pi over 2, the y's will be positive. So that'll be my first interval. Say any x between 0 and pi over 2. And I want to point out to you, I'm going to use a bracket here to include x equals 0, because at x equals 0, the y is positive. Right? Satisfies this inequality. But I'm going to put a parenthesis here, because at pi over 2, the y is equal to 0. And that doesn't satisfy this inequality. This inequality wants it to be strictly greater than. Right? So this first interval, I got a bracket and then a parenthesis because I'm not including that endpoint. All right, now let's come back to this question. So where are the y's positive? So here the y's were positive. We just gave that interval from 0 to pi over 2. And then the y's become negative, so we're not going to list those. And then here the y's become positive again. So when x goes from 3 pi over 2 to 5 pi over 2, any x in that interval, the y's are greater than 0. So I'm going to list that interval as well. Any x between 3 pi over 2 and 5 pi over 2. And again, this is an interval of x values. This is not an ordered pair. This is not an x comma y ordered pair. This is an interval of x values, right? So all x's between 3 pi over 2 and 5 pi over 2 satisfy this inequality. And again, what you're going to notice in my math lab, and you're going to notice in the textbook, is a lot of times they use this union symbol. So this is like the logical equivalent to the word or. So this interval or this interval solves this inequality. All right, now we got one more solution interval, right? So here the y's were positive, then the y's became negative, then the y's are positive, then the y's become negative, and there's one more piece right here where the y's are greater than 0. So as x goes from 7 pi over 2 to 4 pi, right? So these are the x's that correspond to these y's being positive. So I'm going to say from 7 pi over 2 to 4 pi. And again, I'm going to use a parenthesis here at 7 pi over 2 because I don't want it to equal 0. I want it to be greater than 0. Right? And then I'm going to put a bracket at 4 pi because at 4 pi, the y value is greater than 0. So that's part of the solution set. All right? So that's the last question here, letter G for that example. So again, the concept here is we're reading all this information purely from the graph without actually even having the equation for that function. Okay, so let's take a look at one last example. So in this example, we're going to actually have the equation of the function, but we're going to speak graphically about that equation. So the letter A says, is the point 1, 1/2 on the graph of the function? So, obviously I think the easiest way to answer this question is let's plug x equals 1 into our equation and see the y value we get back. If we plug x equals 1 in this equation and we get a y value of 5, then we're going to say this point is not on the graph. Right? So if we plug x equals 1 into the equation, we're going to 1 over 1 plus 1, which is 1/2. So in fact then, this is the point on the graph of the function. Letter B says if x equals 2, what is f of x? Right? What point is on the graph? And this is really asking us to do the same thing as letter A. Right? We're just going to plug x equals 2 in, and we're going to find the point on the graph. So if I plug in x equals 2, I'm going to get 2 over 2 plus 1, which is 2/3. So if x equals 2, y is 2/3, and that is the point on the graph of f of x. Right, and again, just to show you, how we can blend the technology into our work, right? We can kind of check our answers. Let me bring up my calculator, and I'm going to hit the y equals button, and I'm going to type x divided by x plus 1. And one thing I'm going to talk to you about here is when I'm doing fractions, I always want to use parentheses for numerator and denominator. So since my numerator is a single monomial, I don't really need to use parentheses there, but it might be a good habit that I always do. So let me just say always use parentheses around your numerator and always use parentheses around your denominator, right? And this will avoid any errors for typos. Right? So this stresses to the calculator. Here's the numerator, here's the denominator. So if I hit the graph key, right, there's the graph of my function. And if I hit the trace button and I punch in the number 1, I'm going to check letter A for myself. And I'm going to see that the y would be 1/2. So I kind of check my answer to letter A. If x is 1, y is 1/2, and there's that point on the graph. If I hit trace again and I punch 2, and then I hit enter, and I'm checking letter B, and I can see there's 2/3, right? 0.666667 is 2/3. Another way to do this is to go to the table. So I could do, if you notice above the graph button is the table, so I could do second graph, and I could go to the table, and I can see at x equals 1, there's 1/2, and at x equals 2, there's 2/3. All right, I'm a visual person, so I prefer to look at the graph. All right. All right, let's take a look at Desmos. All right, so if I bring up Desmos real quick, and I type, let's say, f of x equals, we had x, I want to punch the x button, and then I'm going to do divide by. And here's what's kind of cool about Desmos is it automatically says, what's in the numerator, what's in the denominator. So I don't need to use parentheses in Desmos. It just assumes and puts the proper form there for me, right? And again, I can click and drag, and not that button. I can click anywhere else on the graph and hold, and then drag to x equals 1. There's my x equals 2, right? And then I can go to x equals 1. and there's that point, right? Or kind of as I showed you earlier, I could just type right here f at 1, and it's going to tell me that value. And I could do f at 2, and it's going to tell me that value. Okay, so back to our example here. So that was letter A, that was letter B, and we talked about using our technology to kind of check those two questions and visualize them. So then the last question says, if f of x equals 2, what is x? What is the point on the graph? So again, notice here, we don't know the x value. And we're being asked, what is the x value, right? What we're being given is the y value. So this is saying y equals 2. What is the x value? So I'm going to literally take my equation up here and I'm going to plug y equals 2. All right? So I'm going to have 2 equals x over x plus 1, and I got to solve for x. All right? So doing the arithmetic of solving for x, I'm going to multiply both sides by the denominator. So I'm going to multiply the right-hand side by x plus 1, and it's going to cancel out. I'm going to multiply the left-hand side by x plus 1, and I get rid of my denominator on both sides. Right? Then I'm going to distribute my 2, so I'll get 2x plus 2 equals x. And then I'm going to subtract this x to this side. 2x minus x gives me the 1x. And then I'm going to subtract this 2 to the other side, and I get the negative 2. So I get x equals negative 2. So basically this is saying if the y is equal to 2, then the corresponding x must have been negative 2. Right, and then again, obviously I can check this on my technology. Right, so again, on Desmos, I can just kind of click and hold my left mouse button, right, and I can drag, and this is like tracing, and I can drag to negative 2, and I can see the y value is 2. I think probably the easier way to check, this is pretty cool, I can just graph, like y equals 2, I can graph that horizontal line. And when I graph that horizontal line, I'm finding that intersection point. I'm finding on this graph where does the y equal 2, and it just kind of highlights that point for me. That's a pretty cool way to do that. All right, so what I want to point out to you here with the TI graphing calculator is that this problem, let me bring up the PowerPoint real quick, right? This problem is not all that easy to check except by tracing. So for example, let me bring up the calculator here real quick, and if I graph, right, so say if I trace and I start hitting like the left arrow, I want you to notice that the x values it's given me are not very pretty numbers. And in fact, if I come over here and I try to I'm looking right here at the y value. If I try to get close to y equals 2, I don't get exactly to negative 2. Well, look, that's really no big deal, right? Because I know the by hand work that I have right here is that x equals negative 2. So what I'm going to do is just hit trace. I'm going to come down here, punch negative 2, and I'm going to say, hit enter, take me to that point on your graph. And that's probably the easiest way to check on my graphing calculator there is just punch the x value and check that number. All right? All right, so in this section, right, quick summary. In 3.1, we had a really long video. We had lots of basics about functions, the equations, domain and range. And in 3.2, this is a relatively short section because we focused purely on the graphical concepts. We talked about the vertical line test, and we just talked about reading information from the graph. Right, as always, if you have questions, please post on the discussion board on Blackboard, and I'll see you in the next video.